Okay, we are on our last section, significant figures, and this is going to be uh, an important section. Uh, I see a lot of students struggle with this. We'll cover it more on Thursday during our lab, um, but this section is significant figures. Um, so let's look at um, this disc here. Oh, she's biting me. Okay, you need to get down. All right. Uh, a Sony, uh, this is a Blu-ray disc, um, and it's a 6 centimeter radius. Um, so that's 6 plus or minus 0.1 centimeters. There, and you'll learn this in the lab. Anytime you take a measurement, there's a little bit of doubt as to what the last digit would be. So this is just a way of uh, representing the tolerance of what you've measured. So the plus and minus 0.1 is a tolerance level. Um, so let's look at significant figures. If you have 1,500 grams, how many significant figures do you have? Well, you only have two. Just the one and the five. The zeros are placeholders. Now, if I were to write the same thing as 1.500 kilograms, the fact that I've placed two zeros after the decimal, that would indicate that those aren't placeholders. Those are significant figures. That would be four significant figures: the one, the five, and two zeros. That would be four significant figures. But here we only have two. Um, and okay, here is exactly what I was talking about. If you have 1.500 times 10 to the 3 grams, that's four significant figures. That what that is saying in a report is that it was measured to that accuracy. Um, if it's 1.50 times 10 to the 3, then there's only three significant figures. And 1.5 times 10 to the 2 is just two significant figures. So scientific notation, as we see in these last three examples, is a way of taking away the ambiguity of how many significant figures are. From just that top one, if we take that top one, it could possibly be four significant figures. We don't know, but the fact that there's no decimal, if you put a decimal place after it, if you put a 1500 point, that indicates that that's four significant figures. But you have to be sure in your reporting that that really is the case. Um, let's look here. 2.3 times 10 to the fourth is two significant figures. So it's written as 0.0023. Now here, the leading zeros are just placeholders. The scientific notation tells you exactly how many significant figures are. So 2.30 times 10 to the minus 4, that's three significant figures. It would be written 0.000230. You have to include that last zero to indicate that it's that many significant figures. Okay, when multiplying several quantities, the number of significant figures in the final answer is the same as the number of significant figures in the quantity having the smallest number of significant figures. The same rule applies to division. So if you have, let's say you're measuring something and you measure 13.5 centimeters, and something is multiplied by 6 centimeters, well, the answer is only going to have one significant figure because you multiplied by 6. That is the smallest significant figure in your calculation. So you have to use uh, the smallest number of significant figures. There's no way to maintain. There's no way to maintain the the three significant figures if you're multiplying by something that only has one. So it has to take the smallest number of significant figures. Um, so you have an area is pi r squared. Now pi, it can be calculated to as many significant figures as you want, but your radius here is only two significant figures. Um, so you can only have, even though pi, 3.14159, and you can go on, even though you can have many multiple digits in pi, you only have 2 in the 6.0. So that would be 1.1 times 10 to the 2 centimeters. So your calculator answer would be 113.09733355. That's not something you want to put down on as a test answer. It would just be 110, or 1.1 times 10 to the 2 centimeters. So you don't just take all the digits available in your calculator. A lot of times you can set to the calculator to 3 significant digits, and it'll give you the answers that most of the time 3 significant digits is a workable amount. Now, as you're calculating, if you're using the calculator, you don't need to re-enter it with just the number of digits. Keep using whatever your calculator says until you get to the end. Once you get to the end, then you can round and use 2 or 3 significant figures, whatever the problem dictates. But don't re-enter your numbers with just 2 significant figures if you're in a continuous calculation. Okay, so continuing with this example, it's not 113 centimeters because you only have 6.0 centimeter in your initial measurement. You have to make it 1.1 times 10 to the 2 centimeters. Okay, when numbers are added or subtracted, the number of decimal places in the result should equal the smallest number of decimal places of any term in the sum or difference. So here we have a 3 digits at 23.2, and we have 4 digits with a 5.174. It equals 28.374, but since we only have 3 significant digits in one of them, we change it to 3 significant digits. 23.2 has 1 decimal place, so the sum is 28.4. Okay, here you have 101, 1.0001. You've got 5 decimal places, and that's 4 decimal places. I mean, but you add them, and you can keep those number of digits. It's showing you that accuracy to the 4th decimal place. If you have 1.002 minus 0.998, that would come out to 0.004. Just that is to the 3rd. Everything is to the 3rd decimal place, and that's fine. In this book, most of the numerical examples and end of chapter problems will yield answers having 3 significant figures, and that's usually a good rule of thumb to use. When carrying out estimation calculations, we shall typically work with a single significant figure. So now this is their rounding method. I use the old-fashioned rounding method. If it's greater than 5, you increase the last retained digit by 1. It's 1.346, rounds to 1.35. They have the last digit is dropped. If it equals 5, increase last retained rounded to the nearest even number. 1.345 equals 1.34. I would have said 1.35, and I'll continue to do that. And he gives a little explanation in the text. I don't remember what he says. I read his text, and he gives an explanation as why he does that. It's just easier for me to just round it up, and you're welcome to do that too. The last digit is dropped if it's less than 5. Leave the last retained as is 1.343. You make it 1.34. I think those first and last rules we're all used to. I guess we would change the first rule to if the last digit drop is greater than or equal to 5, then increase the last retained digit by 1. He gives an explanation in the text as to why he uses this. I don't necessarily agree with it, but that's okay. And that's the end of the lecture for chapter 1. Stop share.